All right, so where we got ourselves to on Friday was thinking about the electrical system of the heart, and we talked about spontaneous depolarizers. So we talked about how we had spontaneous depolarization of the SA nodal cells that would then are electrically connected to the left and the right atrium, so very specifically the atrial myocytes in both the left and the right atria. Okay, so these are muscle cells, so we're getting then, as that action potential is being passed from the SA node to the atrial myocytes, we're going to get contraction of those myocytes and contraction of the left and the right atria, and then that electrical signal moves into the AV node. So if we were to be tracking in terms of steps, we would start with the SA node. We would then move into the left and right atrium with our action potential. We're then electrically connected to the AV node. So we would then see the depolarization and an action potential in the AV node. The AV node is then electrically connected to the bundle of His. The then bundle branches, and then the Purkinje fibers, and then the Purkinje fibers are electrically connected to the left and the right ventricle, and in very specifically ventricular myocytes in both the left and the right ventricle. All right, so because we're passing an action potential on to the ventricular myocytes, so again, this is now muscle. So we are now going to contract the left and the right ventricle as a unit. Okay, so that's just the electrical system that we talked about, and we talked a little bit about at the end of the lecture how, because the SA node has the fastest spontaneous depolarization rate, therefore just based on that sodium leak rate, then it will drive the rate of contraction of the entire heart. So in terms of the progression of the action potential through the system, I've got a depiction of the action potentials down here. So we have been talking in great detail about what makes up the change in membrane potential with the action potential of the SA node pacemaker cell. Okay, and then we talked about how that action potential would be passed on to the atrial myocytes. Okay, so atrial muscle, and then because these atrial myocytes are electrically connected to the AV node, we then see the action potential or a depolarization of the atrioventricular nodal cells, bundle branch, Purkinje fiber action potential, and then finally passed on to the ventricular myocyte. And you can see that each of them have very different shapes. The nodal cells have very similar shapes, but you should be comfortable by now with the different shapes of these action potentials really are just a manifestation of the types of channels that are opening and closing and how long they're opening and closing for. So we're not going to really go into detail about all of these, the channels involved in the development of each of these action potentials. We've already gone over the SA node pacemaker cells. We are then going to discuss in a little bit more detail the ventricular myocyte. The action potential developed there, relate that to contraction because we still have to turn this thing into a pump, okay? So interesting, the velocity at which the action potential can move through the tissues differs a little bit. So it is quite quick, the SA node, how quickly the SA node can move its action potential. When it passes its action potential into the atrial myocytes can pass its action potential across all atrial myocytes wicked fast. And so we need this speed in order to be able to contract both all myocytes in the both atria at the same time, so the thing contracts as a unit, so that you don't get contraction here, then here, then here, then here, then here. But because the action potential is passed so quickly, you get contraction of the whole thing as a unit, right? We need that chamber to contract as a unit. And then the action potential is passed on to the AV node, where it slows down a little bit. And then as we pass on to the bundle of His, the Purkinje fibers, and then the ventricular myocytes, we can see great speed again. Importantly, we get that great speed at the myocyte level because we need both of these chambers to contract as a unit. We don't want some parts of the left ventricle contracting while others aren't. So we need to spread the action potential wicked fast in order to get this whole thing to contract as a unit so we can eject blood. Interesting, we slow the action potential down a little bit when at the level of the AV node here. And the thought here is the action potential slows down just a little bit so that the atria can contract before the ventricles contract. And if we didn't slow it, the thinking is if it wasn't slowed down, the whole heart would contract as one unit because of how quickly it's going, meters per second here. Okay, so it's thought that the AV node slows the action potential down just a little bit in order to allow the atria to finish their contraction, and then the action potential being passed on once it gets into the bundle of His and further down. The whole thing is very quick, and the atria and the ventricles, or the left and the right ventricle then contract as a unit. Okay, so now we know about how we, like the basal rate of the spontaneous depolarizer, and it's just going to do that all on its own, whether with no intervention. Okay, but we do know, you know from anecdotally from your own experience, that your heart rate changes. Excuse me, that your heart rate does change, and so we have to be able to impose on top of these spontaneous depolarizers some sort of control, because let's say you want to go running, you have to increase your heart rate because your blood pressure is dropping, got to increase your heart rate. We have to be able to control that. So we have to be able to control the rate of these spontaneous depolarizers as well. So how do we then control our spontaneous depolarizers? Essentially, how do we change heart rate? So let's think about, let me write in blue here. Let's think about changing heart rate. Right, so we've already built the tools that we have regarding how this cell, the nodal cell, generates its action potential in the first place. So we looked at those channels, and so really those are the only tools that we have to mess with in order to be able to change how this piece of tissue is behaving. Okay, so here's our normal rate. Let's say, let me just make sure you can see. This guy would be our normal spontaneously depolarizing SA nodal cell, setting up a heart rate or a spontaneous depolarization rate of about 70 to 80 beats per minute. Okay, so that's under normal conditions. So we do have direct SNS innervation into these nodal cells. So that means we've got a nerve coming from the coordinating center in the brain, directly coming down and synapsing onto these nodal cells, okay? Which means that we can change their behavior. So indeed, we have sympathetic nervous system innervation, or nerves, synapsing onto those nodal cells. And our sympathetic nervous system releases norepinephrine and is going to increase the permeability of the nodal cells to sodium. Okay, so suddenly we increase the permeability. We had that slow leak rate, but now the leak rate is a little bit faster. Okay, so this is going to increase our sodium leak rate. Okay, and what does this mean then? This means we are going to reach threshold faster because our leak rate just increased. So therefore, we're going to reach threshold okay. Ultimately, this is going to increase our spontaneous depolarization rate, okay, and increase our heart rate. Okay, so you can see that on this graph that what we have here is with sympathetic stimulation, okay, with sympathetic stimulation, our leak rate is faster. So that's the rate we're talking about. It used to be here, right? That used to be our leak rate with just our normal funny current. Now we've got a second current on top of that, so the leak rate is faster. Depolarization is faster, hit threshold earlier, and we get an action potential. Okay, and then again, leak faster, get another action potential earlier. Leak faster, another action potential. Leak faster, another action potential. Okay, so we can effectively increase our spontaneous depolarization rate, which then means increasing our heart rate just through sympathetic nervous system stimulation. So we also know that we can decrease our heart rate. So your heart rate can actually be decreased from your spontaneous depolarization rate. And we do that through the parasympathetic nervous system. So our parasympathetic nervous system, we do have parasympathetic nervous system innervation into those nodal cells themselves. What does that mean? It means a nerve coming from the coordinating center up in the brain, our brain stem, is wired to synapse onto the nodal cells themselves. The parasympathetic nervous system is releasing acetylcholine, and this is going to open acetylcholine dependent potassium channels. So we've got a whole, so this is a ligand gated potassium channel. So we're going to open acetylcholine dependent potassium channels. What's that going to do? We're going to have potassium movement out. If we allow potassium to move, it will move towards its own E ion. Its own E ion is around -100. We're sitting at kind of something around -60. So we're going to get potassium movement out. Okay, that potassium movement out is going to cause a hyperpolarization. A hyperpolarization of the cell. Okay. So now, essentially, we took our normal, let's plot normal on here again. This is our normal action potential, leak rate, which then is going to generate that frequency. Okay? And then with parasympathetic nervous system stimulation, we hyperpolarize. So we took our normal membrane potential, which was, let's say, at some point about -60, and we dropped it. Okay, so now we have the same leak rate, right, but it's going to take us longer to get to threshold because we're further away. So if we went from -60, let's say, to -70, we are just now further away from threshold. And with the same leak rate, it's just going to take us longer to get there. So it takes us longer to get to threshold with parasympathetic nervous system stimulation. Once we get to threshold, that we have our normal action potential. We come back down, though, to a more hyperpolarized state. So now instead of being at -60, we're at -70 again. Just takes us longer with the same leak rate to get to threshold. Boom. Once we get there, though, we get another action potential. At the end of the day, though, it's taken us longer to get to threshold. So we're going to have fewer action potentials per minute, therefore a decreased heart rate. Decreased spontaneous depolarization rate, decreased heart rate. Okay? So let's finish this thought up here. Parasympathetic nervous system releases acetylcholine, opens acetylcholine-dependent potassium channels, hyperpolarize the cell. Let's write it in words. So we take more time to reach threshold. Okay, so we're going to take more time to reach threshold. Therefore, we're going to have fewer action potentials generated per minute. Okay, therefore a lower spontaneous depolarization rate, therefore a decreased heart rate. Okay, so we can, through the sympathetic nervous system and the parasympathetic nervous system, change what our heart rate is. Okay, so this is us thinking about our tool, the SA node, and how it changes heart rate, and thinking of, in terms of, looking at our tool and how can we change our tool. Okay, so the second piece of tissue that we need to think about in terms of changing this piece of tissue that we've been talking about into a pump, now that we've got the electrical system set in place, we need to think about the contractile system. So we need to think about what is actually going to make blood move from one compartment of the heart to another. So we need to think a little bit about the second cell type that we had in the heart. Remember, we talked about two cell types, nodal cells and muscle cells. Okay, so we're going to turn our attention now to those muscle cells. All right, so muscle cells. So we're going to think about the ventricular myocytes. We're not going to think too hard about the atrial myocytes. We're going to head right into thinking about our ventricular myocytes in terms of their action potential, but do know that their muscle cells are both in the atria and the ventricle. So in terms of how we then convert an action potential into force, all right, that's what we need to do to make this thing pump something. We have to think a little bit about the action potential first, and then why we even were trying to get an action potential in this thing to then develop force. So let's think about the action potential. So we have a resting membrane potential of around -90, and it is flat. So this means it's not a spontaneous depolarizer here, right? It's sitting waiting for an action potential to come along. It's waiting for those Purkinje fibers to change their membrane potential, and these guys are electrically connected to those. As soon as the Purkinje fiber changes its membrane potential, that's going to lead to a change in membrane potential in this cell, in the ventricular myocyte. And as soon as we start to change membrane potential, we're eventually going to hit threshold for a voltage-gated sodium channel in this case. Okay, so we are going to hit threshold for a voltage-gated sodium channel. Okay, so we open our voltage-gated sodium channels right here. Okay, voltage-gated sodium channels open, we get this massive depolarization, okay, and then those voltage-gated sodium channels inactivate. Okay, open voltage-gated sodium channels, sodium rushes in, trying to reach Sony ion of about +60 or something. It would reach the +60 if we left it open long enough, but we didn't. The voltage-gated channels inactivated, which means they're no longer fluxing sodium, and we can't reopen it. Okay, so that's why we stop that depolarization. All right, and then we start to repolarize a little bit. This repolarization is due to potassium movement out. Now, we didn't use a specific channel here. It's just that potassium will move out because it has its concentration gradient favors that, and its electrical gradient favors that, and the membrane has a permeability to potassium. So we're going to start to see potassium flux out. So potassium movement out, not due to opening or changing channel, behavior, but just due to a concentration and electrical gradients. Okay, now you didn't see this happen before in an action potential of a nerve or a muscle, because the action potential of a nerve or a muscle was happening so quickly. This you couldn't actually even this event couldn't even happen. But because this action potential is happening over hundreds of milliseconds, okay, that you'll actually be pushing other ions around. So if we think about the timing here a little bit, put a timeline on what we're talking about. Indeed, we are talking about an event that is about 300 milliseconds. So this is time in milliseconds. Okay, so let's just like 100, 200. It's a 300 millisecond event. So moving one ion will now push other ions around if there's an inherent permeability to that ion, which there is for potassium. Okay, so we get a little repolarization due to potassium flux. But while we were rapidly depolarizing due to the opening of the voltage-gated sodium channels, we hit threshold in here somewhere for voltage-gated calcium channels. All right, so those voltage-gated calcium channels are a little bit slower to open. So along here we're opening them, and then we start to have calcium rush in. So we start to depolarize due to calcium. So you kind of start to see this secondary depolarization occur because calcium is now coming in. So somewhere along here, we open voltage-gated calcium channels. Okay, so I'm going to put an arrow around here somewhere because here is where we start to see it manifest, but just know it happened over here somewhere. So we open voltage-gated calcium channels. Okay, so we get calcium movement in. Okay, this is critical. Calcium movement into a muscle cell. Okay, so this should tell you something. We've got calcium movement into a muscle cell. Calcium is the reason actin and myosin interact, and we get shortening and contraction. Okay, so this calcium movement in is actually trigger calcium. Do you remember back in Human Phys 1 we talked about trigger calcium coming in, opening a voltage-gated calcium channel, getting trigger calcium in. That trigger calcium produced calcium-induced calcium release from the SR in a myocyte, and that calcium from the SR went to the actin, or to the cross bridges where it promoted actin-myosin interaction and contraction. Okay, so that's real short synopsis of how a myocyte contracts. It all started with trigger calcium, opening voltage-gated calcium channels. This is them right here. So pretty much the whole reason for trying to get this muscle cell to depolarize was so that we could open a voltage-gated calcium channel and let calcium into the cell. So in essence, this is trigger calcium. Okay. So this is going to be for that calcium-induced calcium release for contraction. Okay, so now the muscle is going to be contracting, or start to get the machinery up and running for contraction. Meanwhile, back at the membrane, we have a depolarization, a secondary depolarization due to that calcium coming in. Okay, and then we don't achieve a huge depolarization because potassium is moving out at the same time calcium is moving in. So you get this switching of the ions, right? So you don't get this huge manifestation of a secondary depolarization as calcium tries to move towards its own E ion, which is about plus 120. So potassium is countering that. It's depolarizing as calcium is, or it's repolarizing as calcium is depolarizing. So they seem to be moving at the same rate because we get this plateau region. Okay, so classic plateau region. Because calcium is fluxing in, while potassium is fluxing out. Okay, so we get this plateau region. And then somewhere along here, voltage-gated calcium channels inactivate. All right, so they inactivate, so they're no longer fluxing calcium, but we can't reopen them again, right? So then we continue to see the effects now of that potassium movement out due to its concentration gradient and electrical gradient, okay? So this region, this repolarization that we're seeing here, is because we have potassium flux out is now greater than the calcium flux in because we inactivated those channels. Okay, so we're heading down to repolarize. Somewhere in here, there's a little bit of a region here where our voltage-gated sodium channels close. Okay, voltage-gated sodium channels close. Okay, and then again, like in the SA nodal cells, in order to be able to produce another one of these, not only do we need those voltage-gated sodium channels closed so we can reopen them, we need these voltage-gated calcium channels closed so we can reopen them. So in this region, so 300, there's another period over which at some point here, over this range, voltage-gated calcium channels will close. Okay? So again, that critical to those, as in our discussion with the nodal cells, is they create these refractory periods. Okay, so there will be a region at which we can't generate another action potential at all because all the sodium channels are in their inactive state. Okay, so that's going to put us out to about here. Okay, so we have an effective refractory period. This is akin to the absolute refractory period you've talked about, and in a minute we will talk about why we keep calling it effective in these cells. Okay, so I've got an effective refractory period. There'll be a period at which if we had a stimulus greater than the original, we could probably get another action potential generated, but it'll look weird. Okay, there's this other than post-repolarization refractoriness, post-repolarization refractoriness period happening, right? Again, we're waiting for those voltage-gated calcium channels to close so we can open them again and have something that manifests itself to look like that original action potential. So really, in terms of the, I'm going to zoom out here for a little bit and see all this. Same page, we are talking about instantaneously making the membrane permeable to sodium and then instantaneously making the membrane permeable to calcium. Okay, so if we were to think about a relationship, there's something else going on here that I just need to show you. If we were to think about a relationship or between the permeability of what's going on up here over time, so let's label this ion conductance. Did I get that right? I'm going to mess it up a bit, but ion conductance or permeability. Okay, over time. Let's extend that out. Okay, that we do have to become, or we do see that we become instantaneously permeable to sodium for a very brief period of time, right? So if we were looking at the permeability to sodium, we would open voltage-gated sodium channels, get this wild increase in permeability, this wild flux of sodium, and then they'd become inactive, and then the permeability drops back down. Right? So that would be what sodium would look like if we thought about its permeability over time across this thing. Okay, calcium, at some point we would, if I just line up about where voltage-gated sodium channel or calcium channels would start to open, they would be starting to open around this region, right? So we would start to open them and then they close or inactive over here. Okay, so we will start to see some sort of permeability. They're slower to open, they're slower to close. Okay. So that would be our calcium permeability. Because this action potential is so long, we have to be very careful of that potassium flux. Okay, so that potassium flux that we talked about right here, we have the potential to lose huge amounts of potassium from this cell. So the cell protects itself a little bit by actually decreasing the permeability to potassium. So if we looked at what the permeability to potassium was over time, at some juncture we would see, once we start to see potassium movement out just due to its concentration gradient and its electrical gradient, there are channels that we close so that we have a lower permeability to potassium. And then when the membrane potential is back to normal, the permeability goes back to normal. Okay, so we're actually having channels in there that we're shutting down. So like you can open channels with voltage, you can also close channels with voltage, right? That's not a stretch to think that we could design a protein, or a protein could be designed to do that. And the reason that potassium permeability drops across this whole thing is so that we don't lose so much potassium because of this passive movement out, because we are depolarizing this cell for such a long period of time. Okay, so we do need to protect ion movement simply because of how long these action potentials are going on. So let's just write that we must decrease potassium permeability to prevent excess potassium loss from the cell. Okay? All right, so we can get an action potential going in this thing, open voltage gated sodium channels, open voltage gated calcium channels, and then that calcium acts as trigger calcium to promote calcium-induced calcium release, and that calcium-induced calcium release from the SR. That calcium moves towards the contractile machinery of the myocyte and gets actin and myosin together, sliding filaments. We get shortening. Okay, so if we were actually to superimpose what was happening as a result of this calcium-induced calcium release here, okay, it would be force. So at some, the axes are all wrong, but I just want you to relate this action potential to force generation. At some point, as soon as we start getting that calcium coming in, we are going to start generating force. All right, so if we were thinking about our myocyte, we would be generating force in there somewhere. And that's how essentially this, we're changing this electrical signal into a mechanical signal. Okay, and that's what we need to make the pump. Gotta have that mechanical signal, or that electrical signal translated into something mechanical. Okay, so before we go and actually think about that pump and how it's generating pressures and all that kind of stuff, let's just return back to this, because I've mentioned an effective refractory period a couple times, so just let's just return to that for a second. So the effective refractory period. Why do we keep calling it an effective refractory period and not an absolute refractory period? Okay, why do we keep doing that? So it's because of something very interesting that these cells can do. So if we think about, so I've got a little data here. If we think about the normal cycle, or let's say the action potential duration, and so they've got that shortened here. This is the action potential duration. Okay, so just the sheer duration of that action potential. Okay, so this is our APD, all right? And at with a certain action potential duration, at a certain heart rate or contraction rate, you will have a certain period of time between contractions, right? So that's dictated by what the heart rate is. So this is the CL, the cycle length, they're calling it here. So that's just basically saying at a certain cycle length, which is really at a certain contraction rate, you have a 200 millisecond action potential duration, of which part of that will be the relative or the effective refractory period, right? So from our last overhead, we could kind of shade in where the effective refractory period would be when the action potential duration is 200 milliseconds. Now, if you speed up the cycle length, shorten the cycle length, which essentially means speed up the heart rate. So let's go to an extreme. Right, so if we shorten the cycle length, right, so if I increase my heart rate, I'm going to decrease my cycle length, right? So the length between contractions will be reduced. Suddenly, my action potential duration drops. Okay, so my action potential duration now is less. It's shorter. It used to be 200 milliseconds, now it's 130. So that means that the duration, the effective refractory period, so the period in which you can't generate another action potential, is now shorter as well. Okay, so this is why they call it an effective refractory period and not absolute, because it's not an absolute period of time. In skeletal muscle and nerve action potentials, it is an absolute period of time and it doesn't shorten or lengthen. Here, because the action potential duration is shortening and lengthening, then the time that it is in its refractory period is shortening and lengthening. So instead of being an absolute period of time, it's just an effective period of time. So that's why they call it an effective refractory period versus absolute. Now think hard, though, not just about the terminology, but about what that just meant. That meant that all of the events that we have just talked about, how long it takes something to open, how long it takes it to inactivate, how long it takes it to close, and we talked about these as timed events the other day. Suddenly, when I speed up how many times the action potential is coming to this cell, all the events happen faster. So this whole thing happens in a shorter period of time. unbelievable. This is where y'all got to get yourself to grad school and figure this out and then come back and tell me. All right? I'm going to give you about 10 years and I want to hear back from you. No idea why and how these molecular events can suddenly be sped up. It's very cool. There's so much we don't know about what's going on here. Okay, so before we leave this section on the electrical nature of the heart, I'm just going to show you a little bit about how you might know the electrical nature of the heart because of more, popular views on how we get information from the body in terms of its electrical nature. So it really is difficult to get a lot of information from a human body, but we can put on electrodes up around the heart and get an external view of all of these changes in membrane potential as they're moving across the heart. So that just happens to manifest itself in something that looks like this, the PQRST wave. This is what the wave looks like, okay? So this is our electrocardiogram, our ECG. So, and if you watch any shows on, medical shows on TV, well, this is probably what you're going to be seeing. So what does ECG do? It tells us about electrical conductance in the heart. Okay, you can kind of get a little bit about the timing of this electrical conduction. The information you can get here, so like, oh, I better write that out, timing of electrical activity. And you could probably get a little information about heart rate from here, okay? So what does this exterior waveform, how does this relate to the electrical events we just talked about, okay? So I'm going to show you them, and then we're going to talk a little bit about what you have to be very careful with when you're looking at this waveform, because this is just, we slapped 3 electrodes on, and this is the waveform that came. So now we're going to relate what these waveforms mean to what the heart is actually doing, what we just talked about, okay? But there's some caveats here. So we note that the P wave is atrial depolarization. So this upward swing is a manifestation of atria depolarization. Okay, so the atria depolarizing, that is, you remember the action potential where it was going from its resting membrane potential to a more positive membrane potential, that shows up here as an as a waveform, okay? The P wave, we call it. So we know if that's atrial depolarization, then right before we see that, the SA node had to depolarize. Okay, so we're not seeing a waveform associated with that in particular, but we know it had to have happened because the atria depolarized. And then we know that after the atria depolarized, it would have handed its action potential off to the AV node, the bundle of His, the Purkinje fibers, and then we get ventricular depolarization. Okay, so this crazy waveform is actually a manifestation of ventricular depolarization. All right, so this is the waveform we get out from our electrodes when the ventricle is depolarizing. And then we get a waveform when the ventricle is repolarizing. Okay. So if this is ventricular, if this is atrial depolarization and this is ventricular depolarization, then we know that in here somewhere we had to have the AV node depolarize or get the action potential. The bundle of His had to get the action potential. Purkinje fibers. The Purkinje fibers had to get their action potential, pass it on to a ventricular myocyte, depolarize that ventricular myocyte, okay, and repolarize. So critical here is that the waveform, amplitude, and direction are all a result of electrode placement. So if this QRS wave, which is ventricular depolarization, was inverted and went down, that would be completely okay. It just meant it was all a manifestation of where the electrodes were placed. Okay, if this was really high, if this QRS went really high, that means nothing. If this T is really high, it means nothing. If the P is really, it means nothing. Okay, so the amplitude and the direction are a result of electrode placement, so those are not data that are helpful in our interpretation of what the heart's doing. Okay, so really critical in how you think about an ECG is to remember that the waveform, amplitude, and direction are a result of electrode placement. Okay, so that's just where the electrodes were. That's why you can't really compare ECGs from one hospital visit to another, because they take the electrodes off and put them on again. So things, the amplitude and the direction will look completely different. What's critical and what you can interpret as data and in terms of what the heart is doing is the appearance of the waveforms and how far they are apart from each other. That's the data that you see. That's the data here, okay? So critical is the appearance, so that the waveforms happened, and the timing of the waveforms. Okay, so the appearance of the waveforms and the timing between them, or of them, is important information from the ECG. Okay, so don't be fooled into interpreting anything other than the timing between them, right? So if this length of time was really long between the P and the QRS, we would know that there is something wrong with the conduction system. It's slower in the AV bundle of His or Purkinje system, okay, if this length of time is longer, etc. So it's that type of data that's here. The direction of the waveforms and their amplitude are meaningless, okay? Below here I've just kind of mapped on so you can see these events occurring in terms of, this is our ventricular myocyte action potential. Okay, so when we talked about depolarization of the ventricle, our QRS wave, so our QRS wave coincides with depolarization of the ventricle, and then the T wave, okay, coincides with repolarization of the ventricle. Again, don't be confused by the fact that both of these go up, because magnitude and direction, or like both of them go up while depolarizing and repolarizing. Again, it's all due to the electrode placement and is not meaningful data. So critical, wave amplitude, direction, or wave amplitude and direction are not something that we can interpret here as what the heart's doing. It's the appearance of the waves and the timing of the waves. All right, so let's just hit that home. by taking a look at a couple of ECGs themselves, just so you're comfortable with this whole idea of what people are actually interpreting when they're looking at these things. And people go to med school for for years and years and years to try to interpret these things. So we're not really expected to be able to do that today. We're just going to take a look at, again, to try to absolutely hit home where the data lies with an ECG. So for instance, here you can see your P wave. Okay, so this is a P wave. We get we got our QRS, and the waveform does look a little bit different. That's fine. I don't care. It's the presence of it and when it existed. And then we have a T wave here. All right, it seems to be bigger than the QRS. Doesn't matter. It's not the data. The really important piece is that right here, between the P and the QRS, between depolarization of the atria and depolarization of the ventricle, there was a delay. That's the important piece of information here. Okay? So what in this scenario, you would say, all right, it looks like the direction and amplitude, that's not meaningful. The timing is we have a prolonged, what they call PR interval. Okay? Prolonged interval between this P wave and the peak of the R, or the peak of the QRS. Okay, so there's a prolonged interval there. So that's going to tell you that there's something going on between with the conduction ability of your AV node, bundle of His, and Purkinje fibers. Okay, this is called first degree block. That interval should be less than 0.2 seconds. Okay, if it's more than that, then you know you've got something funky going on with the conduction system. Okay, and then we can move into second degree block, right, where we've got, here you can see our P waves, you can see your QRS, and it doesn't bother us at all that the QRS is inverted because the direction of the wave doesn't matter. And then looks like we got a T right here. All right, so we can see our QRST, and then we have a P, QRST, or QRS and T, P, QRS and T, P, nothing. Okay, so that's actually a P wave right there. And then nothing. All right, so your heart skipped a beat here. So either something's wrong with your heart, maybe you're in love, your heart skipped a beat. But what happened here was not all P's are followed by QRS's, right? So that means that at this juncture, or at this beat in particular, the depolarization went as far as the atria, and then it didn't get any further because it didn't get into the ventricles to give us that ventricular depolarization and repolarization. Okay, so in classic second degree block, all QRSs are preceded by Ps, so in order to get a QRS, you need a P, all right? That's true. All QRS are preceded by Ps, but not all Ps are followed by QRSs. So again, this does mean that something is wrong with the conduction system between the after the action potentials are handed off from the atrial myocytes into the ventricle, or into the AV node, bundle of His, Purkinje fiber, ventricular system. Something happened there. Okay? But then when the P fires again, or when the atria depolarize again, which means the SA node fired again, then we get a regular heartbeat. But then that does mean, right, that in this period the heart didn't beat, which means the heart didn't eject blood. Right, so a little bit problematic. And of course, the more of these you have, the more problematic it becomes. And then you have something called third degree block, where you can see you've got P waves. Right, so there's a P there, and a P there, and a P there, a little bit of a P there on top of the T, P there all by itself, right? And then you get kind of QRSs. So these P's and these QRSs aren't really even associated with each other anymore. Okay? So it's third degree block is also called complete block. So we can the SA node is firing, and we can stimulate the atria, and they're firing. But then all on their own in some sort of random or in an order unassociated with the P's, we're getting ventricular contraction and QRSs. Okay? So P waves are independent of QRS. Okay? So if we actually had a timeline on here, we would see that we are getting P waves at 70 to 80 times per minute. And our QRSs are going much slower than that. They're actually going at 15 to 40 times per minute. Okay, so based on those two numbers, we could surmise then that the SA node is fine, and it's pacing the atria, but something wrong with the AV node. It's not pacing anybody, but then the Purkinje fibers are now pacing the ventricle. Okay, so you could probably deduce here that there is something absolutely wrong with the AV node and the bundle of His, because the Purkinje fibers have taken over pacing of the ventricle. The SA node is now only pacing the atria. So that means, though, that if ventricles are only contracting 15 to 40 times per minute, that's blood output from the heart, and that's problematic. The heart isn't putting out enough blood now then to actually feed the body, so you can't actually live any quality of life with third degree block. You actually need a pacemaker put in to speed up the pacing of the ventricles in order to get enough cardiac output. But there's two other types of waveforms that we'll look at, because that'll help us a little bit with thinking about what the heart's doing. Okay, so in this scenario, atrial fibrillation. Okay, so that's really just what they're calling it. What you see are QRSs, no P. QRSs, no P. Okay, so we've got lots of QRSs, and then something noisy, and some noisy in between. Okay, so essentially atrial fibrillation, classic. We don't have any P wave, and in fact we can kind of get all noisy in where we should have some constructive P going on there. And what's thought here is that the SA node, at some point the SA node would have fired, and that action potential would have headed on into the atria, and then the atria contract, you get your P wave, and then pass it on to the AV node, bundle of His, Purkinje fibers, then the ventricle, then you get your QRS and your T wave, right? That's optimal. But remember, all of these cells are connected electrically, and that a signal we want it to go in the direction I just mentioned in order to get a nice heartbeat, getting the atria to contract before the ventricles. But we can get an action potential going in the opposite direction as well. You could actually reverse the entire thing. You can get an action potential going from the ventricles to the Purkinje fibers, bundle of His, AV node, atrial myocytes back up to the SA node, because they're all electrically connected through gap junctions. There's bidirectional connectivity. So we connected cells through gap junctions because we wanted really fast action potentials. So we We had to connect them electrically for the sake of speed. So it was good design. But the problem with that is the con you get with that is now action potentials can go in both directions. So problematic is when an action potential is allowed to re-enter the system somewhere. So classic of atrial fibrillation is you have atrial myocytes that aren't contracting in unison. This one's contracting, then that one, and that one, and that one, and that one, and that one. They're not contracting as a unit. And that's because we have some action potential that is firing around there in multiple directions, and you're not getting a cohesive now contraction of that unit. The interesting thing, though, is it's not life-threatening. Many elderly adults live with atrial fibrillation, so you can still have a really good quality of life without the atria contracting. I'm going to hold that thought for a minute until we actually make this heart a pump. I'll actually show you why it doesn't matter necessarily that our atria contract. It is if you're going to want to be a top performer. You can't be an Olympic athlete and have it be an atrial fib. All right, but you can have a good quality of life if you have atrial fibrillation. Problematic, though, is ventricular fibrillation, right? So ventricular fibrillation, here's what the waveform looks like. Really, there's no QRSs, Ps. We can't even see what a P is in there because of this really disorganized electrical activity. Okay, there's no rhythm. Okay, which means we've got some sort of action potential firing around now in multiple directions at the ventricle level. The problem with it happening at the ventricle level is now the ventricles aren't contracting. And when the ventricles aren't contracting, there is no blood pumping to the body. Okay, so this is absolutely life-threatening. You've got about 3 minutes maximum to fix this problem, or else you're dead. Okay, so how do you fix this problem? Well, this is where you get the defibrillator out and put on massive voltages through the heart. Okay, so we're going to have to think a little bit about why that was a good idea to ever do. Defibrillation. Okay, so we're going to put 2 electrodes on the heart and pass massive voltage through. Okay, so why would defibrillation work in trying to get the electrical system organized again? Okay, why would that work? Well, what we're doing essentially is putting one massive action potential, or not one massive action potential, one massive depolarizing signal into all cells all at the same time. Okay, that's never happened before, right? It's always been sequential, but here we're putting it in all at the same time, which means that all cells in the heart are in their refractory periods at the same time. Nobody can go. Nobody can contract. Nobody can pass an action potential. And then who will be the first to start that action potential up again? Hopefully it's the SA node because it's going the fastest. So what defibrillation tries to do is put everybody in their refractory periods at the same time, and then as they come out of their refractory periods, the SA node is the first to fire, and hopefully we get coordinated directional action potentials happening again. Okay, so defibrillation puts all cells of the heart in their refractory period all at the same time. Then the SA node will hopefully initiate the action potential and start organized electrical activity again. So the SA node initiates an action potential. And starts organized electrical activity. Electrical activity. All over again. So hopefully we can get this disorganized waveform back into an organized waveform. Okay? That'll be a good day. Bad day if it stays like this. Okay, so then now at the end of the day though, we have to take all of this electrical information, and we have the muscle, and now we can convert the electrical activity into muscle contraction and force generation, and now we have to turn it into a pump. We've got to turn it into something that can actually move volume from one compartment to another in the heart. Okay, so that's where we need to head. That's where we need to head next. But I think what we need to do, before we think about pressures and volumes and that kind of stuff, we need to go back. I need to go back to the heart here for a minute, the picture, so that we can talk a little bit about the valves. So we had left the discussion about the valves before we talked just about the anatomy in general. We talked about blood coming in from the superior and the inferior vena cava, and we talked about the blood then. So this would be systemic venous blood coming back to the right atrium. Okay, then we know that the SA node is up here, and we would get SA node contraction, or SA node depolarization, contraction of the atrial myocytes. Okay, both the left and the right. And then once we get contraction, we fill this up with blood, then we get contraction, and we want to move blood from this compartment into the left, I'm on the right side, into the right ventricle. And I have to go through a valve. Okay, so the first valve that we have to go through here is called an AV valve, an atrioventricular valve. Okay, a valve between the atria and the ventricles. Okay, critical to understanding this pump is that all valves are passive. Okay, all valves are passive. That means there's no active opening of them. All we're doing is changing pressure on one side, or making pressure on one side higher than pressure on the other side. That's the reason for contraction. I've got this valve, this passive valve. I need to contract to make pressure on this side higher so that than pressure on this side. And if pressure on this side is higher than pressure on this side, I will get flow from one compartment to the other. I will open that valve. Okay, it does look like there's this little papillary muscle here that is desperately clinging on to the to this wall of the valve. So it does look like there's some sort of muscle attached to it. But what's happening here is that these tendons that are connecting the muscle to the valve leaflet are holding on to that valve leaflet for sure, but it's just making sure that this valve leaflet, when the right ventricle contracts, doesn't evert this valve up back into the right atria. So when we contract the right atria, we generate a higher pressure here, open the valve, blood flows from the right atria to the ventricle, which is great. That's the direction we need flow to go. But now the right ventricle is just about to contract because the electrical signal's coming, right? The ventricle is now going to contract. We don't want blood to move, so the pressure here is going to get high. We don't want blood to move back into the right atria. So when we contract the right ventricle, we do then close the leaflets of the valve so that blood doesn't go back into the right atria. But we also can't have that valve and those leaflets evert. If they evert because of the pressure, then blood will flow back there. Okay, so we have these papillary muscles and these chordae tendineae desperately hanging on to the leaflets of the valve, so that the leaflets don't evert back up into the right atria. Okay, so it might look like we've got something to actively open a valve, but we don't. It's just making sure the valve leaflets don't evert. Okay, so we've come from the right atria through an AV valve into the right ventricle, and then as the right ventricle contracts, the AV valve closes, and we generated more pressure in the right ventricle than was in the pulmonary arteries. So we pushed blood through a second valve, pulmonary valve. Okay. And then blood went out to the lungs, and then is coming back from the lungs through pulmonary veins, right and left pulmonary veins. Okay, back into the left atrium. The left atrium, we want to move blood from the left atrium into the left ventricle. Okay, in order to do that, we have to go through another set of AV valves here. 3. This one is given a special name, the mitral valve. Okay, it also has this little chordae, tendonae, and papillary muscles hanging on, so it doesn't evert either when this left ventricle contracts. When the left ventricle contracts, we want to move blood from the left ventricle into the aorta, and right underneath there, you can't see it in this picture very well, but right there is another valve. I'm going to take that out to, let's go out to here, an aortic valve. Okay, so all these are going to open passively. We have to generate pressure on one side, greater than pressure on the other, and as soon as we do that, we open the valve. So for instance, if pressure is greater in the left ventricle, because we're contracting, than the aorta, that aortic valve will open and we will move blood. As long as that valve is open, we're going to move blood from the ventricle into the aorta. As soon as the pressure in the aorta becomes greater than the pressure in the ventricle, that aortic valve closes and we stop movement of blood. Okay? All right, so let me see, should we talk about those here? Yeah, let's talk about those here right now before we move on. 2 ideas before we move on to pressure volume loops. This is the idea of preload and afterload. I hate the names of these because they're not entirely helpful, and the word afterload will confuse us, so we need to get these cleared up. So the preload is actually the volume that the ventricle has. So the volume of blood in the ventricle just prior to contraction. Okay, so just prior to contraction. So when we're filling, let's say from the left atria into the left ventricle, just before this ventricle contracts, it's going to have a volume in it, and that's what we're going to call preload. So afterload is not at all what you would predict it's going to be. It's the load or the volume that the ventricle has to work against. Okay, so what I mean by that is it's the volume, so we've got a volume in the ventricle just prior to contraction, but just prior to contraction too, there's a volume in the aorta too, isn't there? Because it's a closed system, right? So there has to be volume filling all these things. So as this ventricle is filling, there's volume sitting out here. It's not flowing backwards because that valve is closed, that aortic valve is closed, but there's volume there. So that volume in there makes a pressure, right? So that means that this ventricle, as it's contracting, has to generate a pressure greater than the pressure currently in the aorta in order to open the aortic valve and eject volume. Okay, so if the pressure in the aorta is 80 millimeters of mercury, because of the volume sitting in there, when this ventricle contracts, it has to contract more than 80 millimeters of mercury pressure in order to open that aortic valve and eject volume. It's got to create at least 81 millimeters of mercury. As soon as it creates 81 millimeters of mercury pressure, it opens the aortic valve and we eject volume. So afterload is that volume and that pressure in the aorta that the ventricle has to work against. Okay, so that's that afterload idea. Okay, so we are going to come back to both of these ideas when we turn this thing into a pump. All right, so let's start to think then about turning this thing into a pump. We gotta get into the mechanics of it, right? So we've been to the electrical piece of it, let's get into the mechanics. All right, so the mechanics really boil down to a pressure-volume relationship. Okay, so what we're gonna look at here is left ventricular pressure. We'll think about the left ventricle, and we'll deal with the right ventricle in a minute. And left ventricular volume. All right, we're going to look at volumes and pressures. So pressure-volume relationships in the ventricles. Okay, pressures are relative to atmospheric. Okay, 760 millimeters of mercury, so we're going to set atmospheric pressure to 0. So we're going to start out at pressures like 0. Okay, so our pressures are relative to atmospheric. And we're going to set, like we always do, this is nothing. We always talk about pressures above and below atmospheric without really thinking about the 760. We set atmospheric pressure to 0. So set atmospheric pressure to 0. So then we're going to start talking about 0 or like 120 millimeters of mercury or 80 millimeters of mercury, and that is taking atmospheric pressure into account. Okay, so pressure-volume relationship. So here's our shape when it comes to pressure in the heart, left ventricle, and volume. Okay, so we are going to then we will think about putting the electrical and the contraction together. But this then is the manifestation of that electrical system stimulating the contractile system. And once we get the ventricle contracting, what are we doing? We're contracting on a volume, right? As soon as we get contracting on that volume, we want to eject it out of a valve, okay? Essentially what we're doing. So let's think about the pressure-volume relationship here. Essentially, we got to start somewhere, so let's start in diastole. The fancy name for when the ventricle is relaxed. Okay, so the ventricle is not contracting, so it hasn't gotten an action potential yet. So at this time, the ventricle is filling. Okay, so we are seeing a volume in this ventricle. Okay, and then the SA node fires, okay, and you get atrial contraction. Right, atrial contraction. So right here, we're going to get atrial contraction. So we see a little bit of increase in volume, in pressure, atria contracted, a little bit of, and then emptied its volume into the ventricle. Okay, so the ventricle, we will see this little bit of volume and a little bit of pressure. Okay, so remember, we're thinking about the ventricle compartment here, the left ventricle compartment. SA node generates an action potential, hands it off to the atria. The atria have a volume in them, the atria contract. That volume then opens the AV valve, dumps volume into the left ventricle. So in the left ventricle, we should see an increase in volume, and that increase in volume should result in an increase in pressure. Okay, so we see it right there. We see an increase in volume in the left ventricle and an increase in pressure in the left ventricle. Right? Then the action potential moves to the AV node, down the bundle of His, Purkinje fibers, the ventricles get it. The action potential, ventricles depolarize, let in calcium, and we get ventricular contraction. All right, ventricular contraction. So this is also called systole. All right. Ventricles now contract. So we're going to see an increase in ventricular pressure. Right, because we're contracting against a volume of fluid. We're contracting against the blood. So we should see an increase in pressure. This increase in ventricular pressure is going to close that mitral valve. Close that mitral valve. Okay? When we close that mitral valve, we are going, blood cannot now go from the ventricle back into the atria. So that's good. Right? But we haven't generated enough pressure to open the aortic valve. Right? So because the aortic valve, because the aortic valve is not open, we can't move any volume. So both valves are closed around the right ventricle. Okay, let's just quickly. We're contracting here. The mitral valve closed. The aortic valve is closed. So we are contracting against constant volume now. Volume's not moving anywhere. We can't move any volume, especially out of the into the aorta, till we can open up that aortic valve. We can't open up that aortic valve until pressure in the left ventricle is greater than pressure in the aorta. All valves are passive. All right? So we get this period where we are contracting and no volume is moving. Okay, so it's called isovolumetric contraction. So right here. Okay, so right there. Isovolumetric contraction. We're going to get an increase in pressure with no change in volume. Okay, increase in pressure, but no volume's moving. Volume is just sitting constant. Volume is not going to move until we can open that aortic valve. Okay, so we haven't generated enough pressure yet. So aortic pressure is still greater than ventricular pressure at this time. Okay? We have to continue to contract to generate enough ventricular pressure to overcome aortic pressure. I've got a little dotted line here to indicate what aortic pressure is. So we should fully expect that when ventricular pressure goes above aortic pressure, which is going to be about 80 millimeters of mercury, that aortic valve opens and we eject volume. So we will lose volume because it's going out into the aorta. The aorta is getting higher in pressure because volume is going there. Okay, we're going to leave it here for now and pick up this in the next lecture.